Okay, so we are going to look at a problem that asks us to take a distributed load that's on a cantilevered beam and determine the equivalent resultant force and where that force is located on the beam. So I have a distributed load whose magnitude is defined by this equation, x squared plus 10 in pounds per linear foot. So at x equals 0 feet, my distributed load is 0 plus 10, so 10 pounds per linear foot. And when x equals 5 feet, my distributed load is 5 squared plus 10, so 35 pounds per linear feet. And it's parabolic in between. And what we're trying to do is develop an equivalent system that has a single point force resultant at a specified distance d so that these two systems are equivalent. So we know that the magnitude of the force is the area under the loading curve. So mathematically we can write that as force resultant is the integral over the length w of x dx. So for our specific problem, we have the integral from x equals 0 feet to 5 feet. Wx is x squared plus 10 dx. So it's a straightforward integral, and we find that we end up with the following result. Evaluate it at 0 and 5 feet. And we find that our force resultant is 91.7 pounds. Okay? So the next phase is, well, once we know this force resultant, how do we determine d, the distance? So we have a similar equation where the distance d is the integral over the length x times our distributed load, dx, over the force resultant. So you'll note that the denominator is just the force resultant we just calculated. It's the exact same equation. And we know that's 91.7 pounds. So if I calculate the numerator, I again integrate from 0 to 5 feet. I have x times wx, which is x squared plus 10 dx. And we can write that as 1/4 x to the 4th plus 5x squared evaluated at 0 and 5 feet. So again, this is just the numerator because we already know the denominator. So we can evaluate this, and we find this to be 281.25 pounds per foot. So our actual value of d, right over here, is 281.25 pounds per foot. I'm sorry, pounds foot, divided by 91.7 pounds. So we have d is 3.07 feet. So we know the place, the centroid of the uniform parabolic, we know the distance to the resultant force to make these systems equivalent, and we know the force resultant to be 91.7 pounds. So we've solved everything we're asked to solve. And when you solve these types of problems, you should take a step back and say, okay, well, does this actually make sense? You know, if you just look at the shape of this parabolic curve, where's the centroid? I mean, you would think maybe somewhere around here, right? So it's going to be, you would expect, greater than 2.5 feet, right? And that's what we have, something greater than 2.5 feet. Okay, so the location of the centroid seems reasonable. What magnitude seems reasonable? Well, if I took kind of a lower bound and said, okay, well, what's the magnitude of this force? It's 10 pounds per linear foot times 5 feet, 50 pounds. Okay, well, what if I took an average of 10 pounds per linear foot plus 35 pounds per linear foot, divide that by 2, So what is that, 22.5 pounds per linear foot. So the force resultant for this kind of approximate rectangle is 22.5 pounds per linear foot times 5 feet. So an upper bound would be about 102.5 pounds force resultant, which again, okay, this makes sense. Our lower bound's 50 pounds, our upper bound's 112 pounds, and these are just estimations, and our actual result was 91.7 pounds. So we can have some confidence in the result that we found.